Good morning, students. Most welcome in the chemistry class. We are present here with the chapter solid state. And this is very important chapter. Students, we should know what is the objective. Why we will study the chapter? Because always we use many solid substances. That's why we have to know about the characteristics, properties, uses. We have to study in this chapter. My dear children, in this chapter, types of solids, crystal structure, elements of symmetry, Bragg's equation, allotropes of carbon, we have to study. Now, in the earlier classes, you have learned the different phases of matter, that is gaseous, liquid, and solid. In the gaseous substances, intermolecular distance is maximum, intermolecular force of attraction is minimum, and liquid molecules, intermolecular force of attraction is medium. In solid, intermolecular distance is negligible. Now, we have to start in the chapter solid substance. If I tell you what are the characteristics of solid substance, my dear children, solid has the definite shape, definite volume, highly incompressible, rigid, constituent particles held closely by strong intermolecular force and fixed position of the constituents. In previous classes, we have learned. Now, important things. First topic of the chapter is types of the solid. And on the basis of the arrangement of the constituent particles, solids are two types. One is the crystalline solid, another is the amorphous solid. Amorphous, amor means no, phos means from. And crystalline solid means regular arrangement of the constituent particles. And it is the true solid. It has definite sharp melting points. It has the anisotropic nature. What is anisotropic nature? The properties like as electrical and optical properties are different in different direction because there is different arrangement of the constituent particles in different direction. It has definite geometry. Give X-ray diffraction bands. Example of crystalline solids are sodium chloride, cesium chloride, etc. Now I am coming to the points. Amorphous. Amor means no. Phos means form. And it has no regular pattern of the constituent particles, no regular but haphazard arrangement of the constituent particles, non-crystalline solids are super cool liquid, no sharp melting point, isotropic. Students, I want to explain here what is isotropic nature. It means that the two properties like at the electrical and the optical properties are same in all the direction. It has no definite geometrical shape, don't give X-ray diffraction. Examples, glass and rubber and plastics. Because glass, rubber, plastic, they have no regular arrangement or systematic arrangement of the constituent particles. Now, types of the crystal structure. Ionic crystals, covalent crystals, molecular crystals, and metallic crystals. Students already have discussed ionic crystals, covalent ionic crystal, sodium chloride crystal. Covalent crystals like as the graphite, diamonds, silicon dioxide, silicon carbides, molecular crystals, hydrogen molecules, oxygen molecules, HCl molecules, ice, metallic crystals, that is sodium, iron, aluminium, copper crystals. Now, ionic crystals. Ionic crystals, hard and brittle solids, high melting point due to strong electrostatic force of attraction, poor conductivity of electricity. Packing of spheres depends upon presence of charged species present, different in the size of the anions and cations. This about the ionic crystals. Now I am coming for the covalent crystals. Lattice points are occupied by neutral atoms. Atoms are held together by covalent bonds. That's why this crystal's name as the covalent crystals, my dear children. It is a hard solids, high melting points, but poor conductivity of electricity. You know, students, graphite is good conductor of electricity, but diamond is not. Because in graphite, there is one free electron per each carbon atom, but there is no free electron in the carbon atoms of diamond. Two common examples, diamond and graphite for the covalent lattice. Molecular lattice already I have discussed. Again I am telling you molecular solids, 3 types: polars, nonpolars and hydrogen bonding, and it is poor conductor of electricity. Now metallic crystals, soft to very hard, lattice points are occupied by positive metal ions and surrounded by a sea of mobile electrons, because metal has the tendency to lose the electrons, and these electrons are the mobile electrons or free electrons. Metals of high tensile strength, good conductor electricity, malleable and ductile. Bonding electrons in metals remain delocalized. High density. Now laws of symmetry, plane of symmetry. How many types of symmetry, my dear children? Plane of symmetry, center of symmetry, and axis of symmetry. Now elements of symmetry. Regular plane of symmetry, 3. Diagonal plane of symmetry, 6. Axis of fourfold symmetry, 3. Axis of twofold symmetry, 6. And center of symmetry is very important, that is 1. Now total symmetry, how many students? 23 symmetry total. Plane of symmetry, just to see the figure. Regular plane of symmetry, 3. Diagonal plane of symmetry, 6. Now axis of symmetry, fourfold axis of symmetry, that is 3, and threefold axis of symmetry by 4 types. So this is axis of symmetry. Now axis and center of symmetry, twofold axis of symmetry, 6. Center of symmetry, just to see 1. Center of symmetry, 1. Now types of cubic lattice, very important things. First one, lattice classification of solid. Second one, types of cubic crystals, 4 types. Simple or primitive type, where all the constituent particles present only at the corners. This is known as the simple or primitive type. Body-centered, BCC, that is particles present at the corners as well as the body center. And third, face-centered, that is particles present at the corners as well as the face. And end face centered, that is in such unit cell, particles are present at the corners as well as at the center of any 2 opposite faces. Now simple or primitive type, just to see, this is simple or primitive type. Here the particle present at the 8 corners, 1, 2, 3, 4, 5, 6, 7, 8. Here yellow colored particle present at the body and the corners. There are 8 corners particular present here. So this is the body centered cubic. Now face centered, total 6 faces. So yellow colors, total 6 particles at the faces, and in the center 6 faces, and at the corners, that is particles are present at the corners, red colored particles, and the 6 faces, that is yellow colored particles present. This is face centered cubic lattice. And end centered cubic lattice, particles present at the corners as well as the 2 opposite faces. A number of atoms per unit cell in the cubic lattice. This is very, very important. Simple cubic lattice, that is 1 atom. 1 atom means that is per corner. 1 total corners 8. And per corner, that is 1 by 8 part of the particles present. So 1 by 8 into 8, that is 1 atom present in the simple cubic lattice. And body centered cell, 2 atoms. That is 1 by 8 into 8 plus 1. Total 2 atoms. Face centered, 4 atoms. That is 6 faces are there. So half into 6 plus 1. 1 by 8 into 8, that is 1. 1 plus 3. How 3? That is in each face half atoms. So 6 faces, so half into 6. Total 3 atoms. And the 8 corners, total atoms 1. So 1 plus 3, 4 atoms. End face centered cell, 2 atoms. How 2 atoms? That is at the corners, 1 atom, and the 2 faces, that is half into 2. So 1 plus 1, 2 atoms. So now students, up to this, you have to know simple cubic cell, how many atoms, body centered cell, how many atoms, face centered cell, how many atoms, and end face centered cell, 2 atoms. Today up to this, next day we will proceed with the other topics. Good day, students.